project is the physics of baseball and softball. And before I start, I want to say a big thank you to Ms. Wilkinson for just helping this whole project, because she was pretty great and kept me on track. So we can start. Next slide. The general differences between sports. So the baseball field is a lot bigger than softball. The bases are 90 feet apart, and the outfield fence is 300 down the baselines and 400 in center. And the infield is also grass. While softball, the bases are only 60 feet apart, the outfield fence is 200 to 225 feet, and the infield is all dirt. For baseball, the pitching mound is raised about 10 inches off the ground, which, that's kind of an estimation because I couldn't find an exact number, but the pitching rubber is 60 feet from home plate. And for softball, the mound is flat and the rubber is 43 feet from the plate. And then obviously for pitching style, baseball throws overhand while softball throws underhand. And you can go to the next slide. So this is kind of a comparison between the two fields, and this I think is in Texas, one of the universities there, and you can just see how much bigger the baseball field is than softball. And then you can see the little grass patch in the baseball field and how that's not there in softball. Okay, next. So these are some physics terms that are going to be used throughout the project, or the slideshow, whatever. Okay. Force is a push or pull upon an object resulting from the object's interaction with another object. Momentum is the quantity of motion that an object has, and it's given by the equation mass times velocity. Impulse is a force applied over an amount of time, and then potential energy is the stored energy of position, and kinetic energy is energy of motion. Next slide. And then Newton's 3 laws. So his first law states that an object in motion or at rest will stay in motion or at rest until acted upon by an outside force. His second law is force equals mass times acceleration, and his third law is for every action there's an equal and opposite reaction. So, okay, now the actual softball and baseball. So pitching is the biggest difference between the two sports. And you can see that they just can't generate the same velocity and spin because baseball is released overhand with the ball released, or the hand is on top of the ball when it's released. And then softball, you can really see in the picture that the hand is usually under the ball when it's released. And because of that, they just can't get the same spin, and they have different paths going into the plate. So softball has the ability to rise, which baseball doesn't, and baseballs can only go down. So next slide. Next, you have pitching reaction times, and for all of these, we're assuming that the pitchers have strides of 6 feet, which means they step off the rubber when they pitch, which affects the distance. So you can see that a fastball for baseball is about 85 miles per hour in high school. That gets to the plate in about 0.433 seconds, while in softball, a 60 mile per hour fastball is really good for high school, and that gets there in about 0.42 seconds. So softball has less reaction time than baseball typically, but then when you get to changeups, for baseball it's about 65 miles per hour, and that gets to the plate in about 0.57 seconds, and a changeup for softball is about 45 miles per hour and gets there in about 0.56 seconds. There's only a 0.001 second difference for that, which is kind of interesting. So next. So a really big part of softball pitching is the rise ball, and the baseball just doesn't have a rise ball, and the reason for the ball rising is called the Magnus force. So you can see in the sketch that the baseball in all 3 pictures is moving at 90 miles per hour, but the one on the left has no spin. The one in the middle has spin of 1,000 RPM, and the next one has one of more distinct. And curveballs have a spin that's perpendicular to the ground, which actually it causes low pressure to one side and high pressure to the other, which makes it curve to the side with low pressure. And then drop balls, like the baseball curveball, have more straight up and down spin and go down. And then pitches that are thrown harder will move more because of the Magnus force. Next. So next is batting, and it's probably the biggest component of baseball and softball. So in this collision, the ball experiences a force for a given amount of time, and that results in its mass undergoing a change in velocity, which can be rearranged into one of the equations that we call the impulse momentum equation. And you can see that down there. Okay, next. So when people are hitting, they're told to follow through, and I was never like explained why you follow through, because you thought like, oh, if I just swing as hard but stop at contact, like it's still gonna go as far. But actually, when you're swinging and follow through, that increases the time of contact between the ball and bat, which according to this equation, it must change like another variable. And it's not force, because that's all dependent on how hard you swing the bat. So instead of changing that, it changes velocity on the other side. So you have a greater change in velocity when you follow through. Next. So conservation of momentum is another big thing in batting. So the ball and bat both have initial velocities before the collision, and the ball's velocity is negative because it's going a different direction than the bat. But then after the collision, both bat and ball have positive velocities, and those velocities are related through the conservation of momentum, which can be expressed in this equation, which I'm not going to read out because it's really long, and that'd be kind of annoying, but you can see it. Okay, next. And then if the net force acting on a system of objects is 0, then the total momentum of the system is constant, which allows us to use the equation that was in the previous slide. And here you can see how the initial velocities of the ball and bat are opposite, but then after the collision they're the same. So conservation of momentum is a really big reason for the difference in hitting for the two sports. So baseball uses a heavier bat and it's swung faster, and it uses a lighter ball that's thrown faster. So through that equation you can tell the change in velocity is going to be bigger. And then softball uses lighter bats and a heavier ball that's thrown slower, so the ball will be slower after being hit than a baseball. And we know that the baseball bat is swung faster just because typically like boys are stronger than girls, and it's just a fact that you can't really change. But that also leads to a difference in the field sizes, because baseballs can be hit so much farther, so it wouldn't make sense to play baseball on a softball field because there'd be so many home runs. And the same for a softball field. Like if you played softball on a baseball field, there would be no home runs ever. So next slide. So around Thanksgiving, I did a little experiment with a hitting camp, and it was for high school girls and boys, and the boys were all mostly juniors in high school, and the girls were all sophomores. But you can see that I tested their exit velocities, just hitting off a tee, and you can see that for every category, the boys hit it harder than the girls. But interestingly enough, I thought that the smallest difference was when we were using a softball bat and hitting a softball, and the biggest difference was using a softball bat to hit a baseball. But it's just weird how even using the same bat but a different ball, there was so much bigger change in velocity between how hard a baseball versus softball was hit. Next. So I was wondering how much force is used when hitting a baseball versus a softball. And based on the graph, we can see that baseballs are hit with an exit velocity of about 75 miles per hour, and softballs are hit at about 59 miles per hour. And then using the rearranged impulse momentum equation, which is the force times time equals mass times velocity. And then assuming that the ball bat contact time is 0.001 seconds for baseball and 0.0012 seconds for softball, you get the equations of those. And you can see that the baseball is hit with about 900 newtons of force, more than the softball. And this is saying that the boys are hitting the baseball and the girls are hitting the softball with a baseball and softball bat. Next slide. So also the material of the bat and the properties of the ball affect how the ball bounces off of it and how far it goes. So for high school baseball, they typically use composite and metal bats, and those are in the top two, and you can see that those are basically the same. The ball bounces off of them the same, and they both compress about the same. But then you get to the softball bat, and you can see that the ball for the softball compresses a lot more than the baseball, which is the reason for the longer contact time in the previous equation for force. Okay, next. So this difference in elasticity of the ball is known as the coefficient of restitution, which is the E equation up there. And baseballs are made to have a coefficient of restitution for about 0.55 for a 90 mile per hour pitch, while softballs are made to have an E equals 0.44 for about a 60-mile-per-hour pitch, which basically means that the baseball will conserve more of its original momentum than a softball. And then we can see that the batted ball velocity depends on the mass of the ball and the bat, the elasticity of the ball, and the pitch ball speed and the bat swing speed, which is all seen in the bottom equation there, which is adding together the E equation and then the conservation of momentum equation. And then next slide. So ball aerodynamics. So after a ball leaves the bat, there's really three things affecting it. The velocity is like the initial speed off the bat, so that's not really changing after it's been hit. But there's also drag, lift, and weight. Next slide. So like I said, velocity depends on the force applied by the batter during hitting, and once the ball leaves the bat, there's nothing else that's propelling the ball forward, only things that can slow it down. Next. So weight is a force that's always directed towards the center of Earth, and it's determined by Newton's second law, force equals mass times gravity. And the mass of a baseball is about 0.145 kilograms, or about 5 ounces, and the mass of a softball is about 1.18 kilograms, and about 6.5 ounces usually, but it has more variation than a baseball. And because of the difference in weight, the trajectory of a batted softball will be similar, but not the same as a batted baseball because the softball is just heavier. And then as the ball moves through the air, the drag resists the motion of the ball and the resistance air resists the motion of the ball and the resistance is called drag. And it's always opposed to flight direction, no matter if it's going straight up or down or sideways. And many factors affect the magnitude of the drag force, including the size and shape of the object, the square of the velocity of the object, and density and viscosity of the air. So another interesting thing that I found out is there's something called the Reynolds number, which is kind of funny. And it is the ratio of the inertial forces to the viscous forces, which is basically momentum versus air forces. So when the ball's in the air, the molecules of it stick to the surface of the ball, and this layer of molecules pulls on the surrounding flow of the air, and the relative strength of these forces determines how the flow moves around the ball. So a higher Reynolds number equals a decrease in drag, and a lower one increases drag. And you can see the equation down there. Okay. And then this is a chart showing how Reynolds number affects CD is drag coefficient. And you can see that for the baseball, it's both at low Reynolds numbers, it has high drag, but then it suddenly drops off, and then it starts to get higher again. So there's a certain speed that a baseball can go, and it'll have the least drag possible. So at lower RE values, the air is smooth and the wake is thick, which makes it have high drag. But then as it increases, the air transitions to turbulent, which produces a thinner wake and helps the ball move through the air easier. But with increasing speed, the wake thickens and the drag increases. And softballs have lower Reynolds numbers than baseballs because of their lower velocities, which means that they have higher drag. And for both baseballs and softballs, Reynolds number increases with increasing speeds. Okay. So next force acting on the ball in the air is lift. And a spinning ball generates aerodynamic lift, which is perpendicular to flight direction. Like drag, magnitude of lift depends on several factors, like the conditions of the air and the velocity between the object and the air. For a spinning ball, the speed of rotation affects the magnitude of the lift, which is also the Magnus force, like in pitching. So this is responsible for the movement of a fly ball, and typical home runs have backspin on them because a ball with backspin stays in the air longer. And people don't know they do this, but it happens pretty much every home run. And then there's also when right-handed hitters hit a line drive down the first baseline, the ball typically curves in the foul territory, and that's because when the ball is hit off the bat, a horizontal spin is put on it. So like a curveball, it creates low pressure to the right of the ball that causes the ball to go foul. Next. So you can see in this graph the trajectories of hit baseballs, And they're all hit with an initial speed of 100 miles per hour with an angle of 30 degrees and 3 feet off the ground. And you can see that with the more spin they have, the higher they go in the air and the longer they stay in the air.